Okay, folks, in this video I'm going to be going over all the waves questions that I could find on the November 2021 DP Physics SL paper 2. And this first one is about a longitudinal wave that's traveling with a speed of 340 meters per second. That's the speed of sound, so it's probably a sound wave. So we're looking at the variation with time of the displacement of a single particle in the medium. So this is not the full wave we're looking at, it's just how one point in the medium is displacing itself over time. Okay, so like a simple harmonic oscillation of a single point. So we can't just read off the wavelength here. What we have to do is first read off the period. That is what we can read off on this graph. So you read off the period and pay good attention to the units, right? We have milliseconds, we've got micrometers as a displacement. So the period is 4 milliseconds, and we want to find the wavelength. Now, a lot of you will be looking up the wave speed equation, and then maybe you will also be looking up that the frequency is the reciprocal of the period. So we have this, and then basically the wavelength is just wave speed times the period. Wave speed was given to us, the speed of sound, and period was 4 milli, 10 to the negative 3 seconds, and then you get the right answer, which is 1.36 meters. There you go. Now, of course, you could work out the frequency first and so on, but this is sort of the most direct way to get the right answer. Okay. Then the next question is, we see another wave now in the medium, so they're going to superpose, right? The net displacement of the medium is the sum of the two separate displacements. So they're a little bit out of phase here, right? They're not completely in phase, they're not out of phase, not completely out of phase, sort of somewhat out of phase. And we have to find the phase difference. So remember that 2 pi radians corresponds to 1 full period. Okay, this is the angular frequency, omega 2 pi over t. We can see that the difference here between the two waves is 1 millisecond. Okay, so they're sort of lagging. One is 1 millisecond ahead of the other. And the period was 4 milliseconds, right? So you can see we're looking at 1 millisecond, which is a quarter of the period. So it's also going to be 1/4 of 2 pi radians. And that's pi over 2 radians. That's sort of the quickest way to just see that. Get sort of awfully technical if you want to give mathematical proofs for this, but just remember this approach that 2 pi radians corresponds to 1 full period. Okay, identify a time at which the displacement of P is 0. Well, we have to look at when do the two separate displacements cancel out, and you can sort of see that that's 1.5 milliseconds, because here we're have one wave is displacing the medium 4 micrometers up, the other wave is displacing the medium 4 micrometers down, so those two displacements cancel out and we get 0. So that is the time at which the displacement, what did I say, milliseconds. So that is the time at which the displacement is 0. Okay, it's not going to be 0 all the time, right? The medium at point P is still oscillating with a given amplitude, and that is what we have to estimate in the next question. So we have to look at, when do we get the maximum net displacement, and that occurs over here at this point. And since we can see it's on this graph, it's 4. Well, then if we add 4 to itself, we get 8, of course. So that looks like it's going to be the amplitude of the net displacement, the resultant wave. So I'm just going to write 8 micrometers. Okay. Turns out that if you actually draw these sinusoidal waves properly, which the IB haven't done, it seems like, then they don't intersect at a horizontal line of 4 micrometers. They intersect at a little bit more than 4 micrometers. So if any student went in and actually drew these sinusoidal variations, then you would get slightly different answer, more like 8.5 micrometers, but they are just asking you to estimate here, so it doesn't have to be super accurate. Okay, then we're looking at a standing sound wave in a tube, half open tube. And we look at this, and we of course immediately have to sort of be able to identify that this is the second harmonic. Okay, we have a node, antinode, node, antinode, right? The first would be just a node at the closed end and one antinode at the open end. And you can see that this is 3/4 of a wavelength, right? So the whole length L is 3/4 of the wavelength. And they gave us the wavelength 1.2. So we get the answer 0.9 meters. Then a particle in the tube has its equilibrium position at the open end. So kind of over here, right there, there's a particle. Right when time is 0, it has displaced itself all the way to the left, right? So when time is 0, because the graph is showing us maximum negative displacement, it's all the way over to the left, right? So it's kind of like over here when time is 0. And then as time goes forward, then it's going to start moving to the right. And then it's going to be all the way over here on the right at its maximum positive displacement when when half a period has passed, and then it's going to go back again. So at the time 1/8 of a period, it's on its way from left to right. Okay, so the direction of the velocity is to the right, and I've explained why. So state and explain. So the velocity is to the right because it is displacing itself from the left, negative displacements, to the right, positive displacement. Okay, one more. Draw on the diagram the standing wave at time 1/4 of a period. Okay, well, 1/8 of a period, it's going to be there. Now 1/4 is half of a half period, right? Or, you know, it's going to be whizzing past the equilibrium position after 1/4 of a period. And all the points are going to be at equilibrium. So we draw a nice horizontal line there. And that is where all the particles are going to be after 1/4 of a period. Okay, that's that. See you later. Bye.